this talk is indeed about a recent series of work on estimation using the MMD distance. Just a few words on introduction, actually, on my center. Indeed, like I joined RIKEN, so it's a National Research Institute in Japan. And the AIP is a quite new center. Actually, it was created like 5 or 6 years ago, exactly, I don't remember. Research center in artificial intelligence, but they are like computer scientists, mathematicians, statisticians, economists. So it's quite wide, actually. I work in the approximate Bayesian inference team with MTCAN. So I just, as the slides will be available online, you have a link to the team. But actually, these work were done with some collaborators outside the team from when I was actually in Paris before joining the center. So my former PhD student, Badr-Eddine, and friends and colleagues, Alexis, Mathieu, and Jean-David. I will explain later, actually, which one was involved in what part of the project. So before I explain actually what I'm going to talk about, I'll just start with a very simple and classical statistical problem as it would be written in any statistical textbook. You observe n realizations of i.i.d. random variables. They take space in R to the d, or actually it can be also infinite dimensional. You can observe curves. Anyway, they have the same probability distribution, P naught. Okay. And usually, what you do when you're doing statistical inference, you propose a model that's a family of probability distributions, and you assume that P naught is in this model. So actually, there is a theta naught such that P naught is equal to P theta naught. And then actually, based on the sample, based on x1 to xn, you want to compute an estimator, theta hat, that must be as close as possible to theta naught. Okay. The point is that I would like to do it in a kind of universal way. That means that I would like to propose a method that will work whatever the model P theta is and whatever the truth P naught is. And what I want to start by claiming, actually, by explaining, even though probably you know it, but is that the most classical method, the maximum likelihood estimation method, actually is not universal and requires strong assumption on the model and on P naught to work. So I remind you, like, just the definition of the MLE. So you define the likelihood as the product of the densities with respect to any measure, actually any sigma finite measure of the P thetas, and then you maximize this quantity. Okay, so very famous example. If you assume that the model is made of Gaussian distributions, then you recover the estimator of the expectation by the empirical mean and of the variance by the empirical variance. Okay, as I said, you need strong assumptions. And indeed, even though this model is maybe not very practical, but it's very easy to build a model. Here, where the MLE will not work. So here, I propose a model which is a translation model. So actually, you just want to estimate a centering parameter. And apart from that, once theta is known, actually, the density is just fixed. There is no shape parameter or variance parameter to estimate. Okay. And the point is here, this definition, this distribution, sorry, this probability distribution, the density is equal to infinity at 0. So it means that actually, whatever the sample you draw, the likelihood will be infinite at each point of the sample. So maximum likelihood is not even defined. And if you take one of the points randomly, you take one of the argmax, sorry, randomly, then you probably will not have a consistent estimator.
Sorry, can I just ask a quick question on that? I mean, I totally agree. Mixtures of normals is a fantastic example to show how maximum likelihood is not a very sensible idea. But when you said doesn't work, what did work mean? Because it does. Sorry, yeah. I mean, under a certain point of view, saying all of them come from one distribution and one comes from the other is actually a sort of, at least it's not a logic. It's not what we would do in common sense terms. but it solves the problem. I think the problem is, or maybe you're saying it too, that likelihood function is basically a flawed idea. There is not a theorem that says having a big likelihood makes something plausible.
No, but here in this case, it's just like, okay, but it does not work. I meant actually not consistent. There are examples where it is known that actually you have one maximizer and it is not consistent. Here, the simple example I show is simply an example where you cannot even define the maximizer because there are like as many, they are exactly.
Surely these functions are positive. Surely the maximizer is in plus infinity, and that's it.
Yeah. Okay. So then actually something else which is quite important, I think, and this will be the, well, one of the main ideas that will come later in the talk, is that the maximum likelihood fails when you have outliers. And well, you know that you propose a statistical model, p theta, and it's not very likely actually that the truth p naught will belong to this model. So there might be slight difference between the closest p theta and between p naught. And for example, like something that is quite popular is to represent like the truth using, the Huber contamination model. So actually where you would have, the model would be in some sense true, like with large probability, you draw someone from the model, an observation from the model, but you have outliers, you have a source of contamination, and with small probability, the point, the xi is not drawn from p theta naught, but it's drawn from a contamination distribution. And here again, like even in quite simple models, like for example in the uniform model. So in the uniform models, if you want to estimate theta in the uniform model on 0 theta, the maximum likelihood is the maximum of the xi's. And if the contamination distribution is anything that is quite likely to draw a point that is larger than theta naught, then actually you will end up with an MLE that is extremely far from the truth. So I just want to make it clear. I'm not saying that one should not use MLE, and I know that these examples are well known, and that the way I apply MLE in this example is maybe a bit too strict. I just want to actually to refer to a kind of, there was a strong movement in the literature for many years to try to define a procedure that would work as well as the MLE if possible, but that would not suffer these drawbacks. And that would be robust to this kind of misspecification problem. Okay, so definition that was proposed actually in the literature is the definition of a universal estimator is that for some distance d on probability distributions, first, it's a special case of what will come next, but it seems important that when the truth is in the model, so p naught is equal to p theta naught, then actually your estimator theta hat satisfies that the distance between theta hat and p naught in expectation will tend to 0. So hopefully I will be able to give a rate of convergence Rn that might depend on the parameter space theta.
Could I ask a question about that actually? Because yes. What would worry me in that is that first of all, you've now introduced a distance on the space where the random variables are taking their values.
So actually, it doesn't have to be a distance, sorry, but yeah, sorry.
And secondly, you could imagine examples where, for example, you could be quite close. I mean, just have why does having the sample measure close to your measure be a good indication that that measure came from the other one? I mean, for example, you might have a random variable that only takes very particular values, and you might know it took this value. So that might rule out a large class of measures that are close.
But first, the point is that it depends what you mean by knowing that that the data comes from this measure, actually. Because of course, like it depends on what you're trying to do. It depends on what is your objective. The distance d should be tailored according to your objective. And you know that, for example, in machine learning, we use a lot of predictive measures. In this case, we don't really care if we estimate the true probability distribution, but we want to estimate at least correctly from the point of view on the predictive performance. So yeah, okay, in this case, it might not be exactly a distance. And actually, I want to say that even though I will only talk about distance in this talk, all these could be discussed with more general discrepancy measures.
Yeah, but it could equally well be a communication channel where you want to recover as a digital signal, and it might be that you put some encoding in. So it might be that your next one can only have certain values given the previous one. I mean, anyway, yeah, I agree. It's okay. It's a sensible thing to do. I'm not disagreeing with that. Okay.
It's okay. I think the question is legitimate, like to try to find an estimator that will do that. And once again, I'm not claiming that this is what should be done in practice all the time. But in some sense, for me, it was frustrating to realize that many methods that I knew would not achieve this. And more generally, in a misspecified case, what I would like to have is in some sense, like if the model is not true, but it's not too far from being true, in the sense that P naught is close from the model P theta, then actually I would like to have an inequality of this type, which is usually referred to as oracle inequality, whereas I would say that the distance between P theta hat and P naught would be close to the smallest possible distance between P naught and the model, that is P theta naught. So hopefully, I just want to make a remark on this. Actually, hopefully, this distance, P naught and P theta naught, when P naught would be written as a mixture of true distribution plus contamination, as in the Huber model, I would like this to tend to 0 and epsilon tends to 0, which will be true or not, depending on the distance d. But actually, if you interpret distance here, not in the sense something that satisfies the axioms of a metric, but something more general, like for example, the Kullback divergence on which the MLE is based. Actually, in this case, when epsilon tends to 0, the KL does not necessarily tend to 0. Actually, it can remain infinite in some cases. So, which explains in some sense some instabilities of the Kullback of the maximum likelihood estimation. So as I said, I want to try to build something that satisfies these requirements. And actually, I want to mention a very nice example that was built by Yatrakos in the 80s. What I wrote is actually wrong in the sense that I really simplified the statement of the theorem. There are some assumptions on the parameter space, but if you use this result in most statistical models, what you will find is that what I required before, that the distance is as small as the smallest possible distance plus a rate of convergence, for Yatrakos estimate, it works with the total variation distance and with a rate of convergence that would be the dimension of theta over n, where the dimension actually is measured in terms of covering numbers. So actually, you need the parameter space to be finite dimensional in this sense, okay? So the paper is quite nice actually, and I don't know if you know this paper or not, it's worth having a look at it. It's only like 4 pages. The proof is quite short and very elegant. But the point is that in the end, it's quite like the definition of the estimator is, it's not even that it's complicated actually, but it's just that it relies on a complete discretization of the parameter space and on an enumeration of all the parameters, a comparison of each one against each other, which actually is not really feasible in practice. Okay. There is a similar result that was done recently by Barrault, Birger, and Sartre with the Ellinger distance. Very nice work, but a bit more technical. And here again, even though like the result is beautiful, there is a problem is that the estimator is usually not feasible in practice. Okay, so I would say that this is actually interesting because in many stats textbooks, the requirement that you are able to compute an estimator is not always written explicitly, which I think is important. So I will also take that into account. And all I will do now is that I will try to propose to use another distance, that's this maximum mean discrepancy distance, that was used actually in statistics for other purposes, in statistics and machine learning until now. But like I will try to use it for parametric estimation in the first part. And even though you'll see that it might look like a dumb ID in the sense that it gives a kind of very simple estimator and very simple results, it satisfies this universality requirement, and it gives nice results, especially in terms of robustness to outliers. And hopefully I will have time to talk to problems of dependence in the observations as well. Okay, so I'll just explain briefly the construction of the estimator, but you will see that it's quite, the idea is simple. So it's just based on kernel methods. So I assume that, but you know, like if you take a continuous function from the space X to a Hilbert space, and then you build K of xy as the scalar product between phi of x and phi of y. So such a function is called a kernel. And kernel methods are very popular in machine learning, but usually they're not defined through the function phi. But it's just that you give a two variables function K of x and y. And if it satisfies the positive definite condition written here, actually, then you know that there is an implicit function phi and space H such that K can actually be written as the scalar product between phi of x and phi of y. Okay, so usually this is actually used for non-parametric methods. I will show you how to use it for parametric methods. So in order to do this, I will require a few assumptions on the kernel. And the first one is that the kernel is bounded, so it's smaller than 1. And the reason why is that in this case, well, if I will define the following thing, I will call mu of p, so that the mean of p. It's the expectation when x is drawn from the probability distribution p of phi of x. And k being bounded, I know that phi, the norm of phi that is actually bounded by square root of k of x is bounded by 1. So actually the expectation is well defined. There is another property called, I will call that characteristic kernel. It says simply that, well, if mu of p is equal to mu of q, then p is equal to q. So it's an injection. Okay. So it might seem a lot, but the point is that I provide here two examples of kernels that are used in practice when the space X is R to the D. So either the Gaussian kernel or the exponential kernel. And both of them are actually bounded by 1 and characteristic kernels. Okay, and the distance that I will use here to compare probability distribution is this simply the norm in the space H of mu of p minus mu of q. So you'll see that actually, if you just take this as a distance and decide to work with this, so I will define the estimator in this slide, but you'll see that the theory of this estimator, like the consistence, can be done just in a few lines. It's extremely simple, actually, thanks to the Hilbert structure. So I just remind the context. x1 to xn are i.i.d from p naught. And I have a model p theta. And I don't assume, of course, I don't want to do the mistakes I made in the introduction. I don't want to assume that p naught belongs to the model p theta. Okay. So I will define simply as usual p and at that the empirical distribution that is 1 over n times the sum of the point mass at each xi. And I define the MMD estimator as the one that minimizes the distance between p n at and p theta for theta in the model, in the parameter space, sorry. So just one remark, there are actually conditions written in order to ensure that this minimizer exists and is unique. But the results I will present later can be extended very easily to the case where the minimizer does not exist. In this case, you just replace it by any epsilon minimizer and the result still holds, actually. So it's actually safer than just having to assume that, that it exists. So I will prove a result. I skipped the lemma, but I will prove the result. I just want to show the theorem first. So don't look at the first 3 lines. This theorem says that actually you have the inequality that I wanted to have, the one that I announced in the introduction, in the sense that under the only assumption that x1 to xn are i.i.d from p naught, the expectation of the MMD distance between p theta at and p naught is bounded by 2 over square root of n, universal. It does not even depend on the size of the parameter space theta, and plus the infimum between between p theta and p naught. So the distance between p naught and the model. Okay, and it appears that this result is just like it takes 2 slides to prove it, and actually it's just because I really write details. Actually, it's quite easy. So there are 2 steps. The first step is to prove that actually Pn at the empirical distribution converges to P0 at rate 1 over square root of n. And the reason why is just like written in these 4 lines. Sorry, it's just that actually, if you rewrite the definition of Pn at, this is simply the computation of a variance of the mean 1 over n sum of the Dirac masses of the xi's. And you just say that variance of 1 over n times the sum is 1 over n times the variance of mu of x1, exactly as you would have in a real case. It works actually. So just like thanks to the Hilbert structure, 3-line proof, and Pn at converges to P0. Okay, so this is not, this is for the lemma, but actually then to prove the theorem, you just have to plug, to use the definition, you start with the triangle inequality. So you use the triangle inequality, and you, so the distance between P theta at and P naught is upper bounded by the distance between P theta at and P at, plus the distance between P at and P naught. And by definition, the MMD estimator, theta at, minimizes the distance between P theta and P at. So actually, you have the second line. And then using the triangle inequality again, you see that you obtain exactly the inequality you want, plus the rate here for now is simply the distance between P at and P naught. But when you take the expectation on both sides, this quantity here in green, you just choose the lemma from the previous slide and you obtain the result. So it's actually, we have an estimator. Whatever the truth is, it will converge to the truth, but in a rather loose sense, I agree with this, like it's just for this MMD distance, but it will converge to this, to the truth. If the truth is in the model, otherwise it will converge to the best approximation. So just a few refinements on this. Using the same proof here, you can control the quantity in green, not only in expectation, but with large probability. So you use, for example, Magyar-Mead inequality. And another statement that you can have is like with very large probability. So with probability at least 1 minus delta, but you can choose delta as you want. And here again, the distance between the estimator and the truth is the best possible one plus a quantity in constant over n. Okay, so just before I give more details on the theory, I just want to explain maybe just in a few lines why this estimator can be computed actually. So why in many models it's possible to compute it. And the reason is that if you come back to the definition of the MMD distance, if you write the distance between P theta and P at, so the one that you have to minimize to compute theta at, you see that it depends on, it's just 3 terms, of course, like because it's a square of a difference in a Hilbert space. So you obtain like these 3 terms. But like the third term here depends only on the data, but not on theta. So you don't actually have to pay attention to it. And the first 2 terms depends on expectations. But what is interesting is that they depend on expectation with respect to P theta and not with respect to the true distribution of the data. Which means that sometimes you can sample from, if you can sample from P theta, then you can have an estimation of this distance. And actually in practice, what we did is that we wrote conditions on the model P theta. So when the density, when P theta have a density, small P theta with respect to a measure, like for example, Lebesgue measure, then you can and that you have some, differentiability assumptions on this P theta. Then you can differentiate this distance, and you have an expression of the gradient of the distance, of the square distance between P theta and P at. And this gradient, same, it's an expectation with respect to P theta. So it means that if you want to have an unbiased estimate of the gradient, you just have to sample a few xj's from P theta, and to compute a Monte Carlo estimate of this quantity here. This gives you an unbiased estimate of the gradient, and you can use stochastic gradient estimator, and it will converge, hopefully, to the minimizer. At least it will converge to a local minimizer of this quantity. I just want to give a few references because actually we are not the first to think about this method. This method was used in a paper written 5 years ago by Twente et al. Where they used it to train generative neural networks. So the idea really was the same. It's just that I don't know why actually I mean the paper has nice experiments on GAN actually, so they used it to generate faces that were not in the sample just based on the sample, but they did not push the theory further, I think, and so more recently there was a paper by some authors from the Turing Institute, actually. Well, they started to investigate this method, not only for GANs, but in general. And they provided the first results. So they had the bound in probability that I gave before, the one based on McDermid. And they also proved asymptotic distribution of the estimator. So I will not talk about that, even though it's interesting, under some nice assumptions on the densities in the model. Your estimator is asymptotically Gaussian. I want to focus on something else, and I wrote a series of papers with the co-authors I introduced in the beginning on this topic. So I just want to explain very quickly what we did in these papers. In the first one, we studied what I will present later, that's the robustness to misspecification and to possible dependence, that is actually misspecification of the independence assumption. The second paper is very short, but it's just an extension to say that we can do kind of Bayesian estimation with this. And more importantly, I think the point is there is a limit to the method I presented, is that you have to specify completely the model p theta. And in many statistical and machine learning problems, we don't specify completely p theta. We propose, for example, in regression, usually you only specify the distribution of y given x, but you don't specify the distribution of x. So it appears that it was possible to define MMD estimator in the case of regression, but because of this, and because we did not want to specify any distribution for x, it would not make sense. It required more work and it's a bit more technical. And the same thing for copula, actually. So we wrote this paper with Jean-David Fermanian and Alexis Derumigny. They are specialists of copulas, model that's used in industry and in finance. The point is here again, in copula, usually you just specify the dependence between two random variables, but you don't specify their marginals. And we wanted to use MMD without having to specify the marginals. So this is the reason why this paper is written, and there is a package actually also coming with this. I will focus on the results of the first paper now. So I just have a few slides to explain the robustness to outliers and the robustness to dependence. I think each part can be presented in 10 minutes. So if you have questions, really, don't hesitate to ask. Otherwise, I will just come back to the Huber contamination model. So,
sorry, I have a quick question.
Of course, yes.
In the parameter estimation that you presented, so your assumption was that the kernel is characteristic, but often it was, a sort of annoying problem in practice is the parameter choice of the kernel. Your RBF, you would have the sigma, and
yes,
you had it fixed. In practice, is there sort of a general strategy?
Okay, so this is, of course, this is a very important question because here I just present the result, and you see, I would say in some sense, sorry, if I come back to, for example, to this theorem, it's hidden. The kernel K, say we take a Gaussian kernel, which, I mean, we should not even take it for granted. Why Gaussian? But say we take it Gaussian, it depends on gamma, and the gamma is hidden in the distance here, which means that if you change gamma, not only you change the estimator, but you change the way you assess the performance of the estimator. So it's really a problem. What I can answer is that first, in this part, robustness to outliers, you will see that we know what should be the optimal parameter. So I will prove it. So there are very simple cases, at least like in the case of the estimation of the mean of a Gaussian. Like in very simple case, we know what is the optimal. Otherwise, you have to use like things like cross-validation or empirical methods. I'm not really sure if cross-validation makes sense in this case, actually. But we did some experiments in the paper on copula, and at least by sampling from the model, it seems that it's possible to have a good idea of what should be gamma. And moreover, what is interesting is that gamma is stable in the sense that gamma doesn't seem to depend on the sample size. And you will see, actually, it's quite striking. But in the example of robust estimation of the mean of a Gaussian, you will see that the optimal gamma does not depend on the sample size. So it's a constant that we have to find once and for all. It's not something that will depend on, that you have to change. On the contrary of what you would do in non-parametric estimation with kernels.
Okay, thanks. So the reason I ask is already when you do hypothesis testing with these MMDs, then this parameter choice becomes super tricky because you can't do cross-validation anymore, and then there are a lot of recipes you find out there, and I don't know. Not all of them,
they also have, like in the paper on GANs, they have well, a heuristic to choose it that seem to give good results in their experiments. But like, of course, there is no. It's quite complex, so there is no theoretical justification for it now. Still, I hope to convince you that something should be feasible by the next example.
Okay, thanks a lot.
So I come back actually now to this, and you will see the connection with gamma soon enough. I wrote, as a reminder, the theorem that I just proved a few minutes ago. And I will apply it in the special case of Huber contamination model. So P naught is not exactly P theta naught, but it's a mixture of P theta naught with large probability and the contamination distribution Q with small probability. In this case, because the kernel is bounded, actually, and using, again, the triangle inequality, the distance between P theta naught and P naught is actually bounded by 2 epsilon. And you can do the same, actually. You can upper bound the distance between P theta at and P theta naught, sorry, in the same way. So actually, it's quite easy in some sense to obtain an upper bound here on the distance between P theta at and P theta naught. So if you assume that, once again, P theta naught is not exactly the truth, but it's not far from the truth plus a contamination, the level of the contamination is epsilon. That is that the probability that given sample is not drawn from the P theta naught, but it's drawn from the contamination is epsilon. Then actually the expected distance between the MMD estimator and P theta naught is smaller than the rate, 2 over square root of epsilon plus 4 epsilon. And I think that this result is interesting. It has been actually in the past 2 or 3 years a regain of interest in robust statistics, and many papers appeared actually where people studied various models, and they tried to study the optimal dependence of the estimator as a function of n, but also as a function of epsilon actually. So as an example, I will consider here very simple model, the estimation of the mean of a Gaussian when the variance is known. So say that the variance is 1 if you want. We just want to estimate the mean. It appears that the calculations are, well, it's a bit heavy formula, but actually it's just like Gaussian integrals that are quite easy to do. So the MMD distance between 2 parameters, theta and theta prime, can be computed explicitly. It depends on sigma squared, but we assume that we know it, and it depends on gamma, that we don't know. We don't know which one to choose. But the point is that if you plug this into the previous theorem, what you can do is, instead of having a bound on the distance between P theta at and P theta naught, you can reduce a bound between on the distance between theta at and theta naught. Okay. So actually, you obtain from the previous that the expectation of the distance between theta at and theta naught is upper bounded by this. So it's just an inversion of the formula above. And So, well, maybe it looks a bit complicated, but like it's a log of 1 minus something. And this 1 minus something is essentially the constants times 1 over n plus epsilon squared. So when epsilon square is small and 1 over n is small, because n is large, the sample size is large, this is close to 0, and this is fine. So the square distance, for example, when epsilon goes to 0, the square distance goes to 0 at the rate 1 over n. So we're quite happy with this. But now it appears that it is known that the minimax rate of convergence in this problem is d over n. And what we found is that actually if you take gamma equal to 2d, d being the dimension of the parameter, sorry, theta is in r to the d. If you take gamma is equal to 2d sigma squared, then actually you obtain the following result, which is that the expectation between of the distance, square distance between the estimator and the truth is upper bounded by d sigma squared over n plus d sigma squared times epsilon squared. So, comment on this result. First, when epsilon squared is equal to 0, so when there is no contamination, you obtain the minimax rate of estimation in the Gaussian mean model. So it seems good. The other point is that when you add to this a small proportion of epsilon, of outliers epsilon, your estimator remains good, at least when epsilon is not too large. Still, it's not completely satisfying in the sense that in the recent papers I just mentioned before, it's known that the optimal rate of convergence in this model is not d over n plus d times epsilon squared, but it is d over n plus epsilon squared, which means that our estimator is optimal in small dimension when d equals 1, but when d is large, it's no longer optimal. It's not robust enough in some sense. Still, we were happy to see that we can, at least in some cases, recover the optimal rate. And also, once again, this method is universal. So this method does not have to be used only for Gaussian estimation. It can be used also for any parameter estimation, while actually the method that reaches the rate d over n plus epsilon squared, this method is, of course, relies very strongly on the Gaussian assumption. So if you want to be more general, then maybe you have to lose something somewhere. We did some simulations, just like the first series of simulation here is not extremely fascinating because it's quite expected. I just sampled from Gaussian distribution with fixed variance. I want to estimate the parameter theta and 200 observations. And when the truth is actually in the model, so there is no outliers, you see that the mean squared error, mean absolute error, sorry, of the MLE 0.07 and of the MMD 0.08, which is expected, of course, because there is a nice theory of maximum likelihood estimation, which tells you that asymptotically the MLE is optimal. It has the smallest variance when some assumptions are satisfied, but these assumptions are satisfied in the Gaussian model when it is well specified. Still, just of course, replace 2% of the observations by drawing from a Cauchy distribution. And of course, immediately the MLE, which is just the empirical mean, is destroyed by that, while the MMD remains almost the same. And just here, another contamination by a constant. Here again, the MLE is destroyed and the MMD remains the same. Maybe it seems a lot of talk just to do something that we could have done with the median, because actually I did not represent the median here, but I hope that you, we are trying to estimate the centering parameter in a robust way. The median works. I did not even write it here, but it has similar performances to the MMD actually. So of course, the MMD does something nice, but that we already knew how to do. However, we studied other models, and I mentioned our paper on copulas, for example. So here it's Gaussian copulas, and the 3 different graphs correspond to 3 different types of contaminations. And we like the level of contamination is between 0% and 5%. And you see that the MLE here is in red is the best estimator that we tested in case of for the Gaussian popular parameter. So it's a covariance parameter here. It's the best one when the contamination is small, but as soon as the contamination is above 2%, then the MMD estimator, like we tried 2 different ones, become better in blue and in purple. But with some other contaminations, actually, it's a bit more spectacular, and the MLE becomes very wrong with just 1% of contamination, while actually the MMD estimator remains correct. You could argue that this is still simply the estimation of a covariance, but then we did the same experiment for other popular models, for example, Clayton, Gumbel, Frank, and in this case, the parameters are not immediately written as covariances, and we have similar results. Also, yes, sorry.
Sorry, no, finish with you. I'd just like to ask a question in a minute when you're at the appropriate point. Sorry.
Okay, no, I just wanted to say actually that we have also, even though we, I did not include them in the slides, but a few simulations in the regression model. And you can check it's quite similar actually. So in the regression model, either linear or logistic, the estimator is quite robust, and it's quite robust to a contamination either in the distribution of Y or in the distribution of X. So this is something that seems to, like in practice, in all the models we tried, it seems to work constantly. Actually, this is the end of this part. My next part is about a completely different topic. So if you have questions, maybe it's.
Yeah, could I ask you a question? I mean, if one's using maximum likelihood and one has a model which is based on normal type variables, then one really expects it to go wrong because most random variables have longer tails, your outliers. I understand that. But the way I would have historically, 20 years ago, would have handled it, would have said I should have taken a model with longer tails. And so my question is, suppose you hadn't taken your model to be Gaussian, but Cauchy, say.
Yes.
And then you've done whatever people would normally do. Would you have got a better answer than the Gaussian too? I guess you probably would, actually. You see, the point is that the Gaussian is so unexpected to see tail behavior that if you get any, it's going to dominate the whole analysis of what's going on.
Yes.
But that's a flaw in using Gaussian models. I mean, the central limit theorem doesn't tell you it's Gaussian in the tail; it tells you it's Gaussian in the middle, and so it's not surprising that, you know, there's no modeling fact out there that says you should be using Gaussian things. People do it, but that's because they like something with 2 parameters. But if you suppose you changed your model so it allowed more tail behavior, what would have happened?
I cannot say exactly what would happen if I had used a Cauchy model instead of, or for the tails at least. Maybe you could have had the same results. Once again, I mean, it's nice that we have this procedure that is just one procedure and that does that in some sense automatically. Now, the question is, I mean, like, of course, what you say is when the problem is essentially in the tails. And in this case, there's been a lot of work, of course, like on trying to use, so like many interesting papers recently on different way to avoid this problem in the tails with the median of mean methods, with the change in the loss function, or using a robust loss function like Huber loss. But
I guess my question is just, doesn't it make sense just to have a model that's compatible with the data? The Gaussian model is not compatible with having outliers.
Yes, but the point is that first it's compatible with the data, which means that it's built after seeing the data, and then actually once again, like you mentioned the problem in the tails, but you can have other problems that would be problems in the support of the distribution. So actually outliers are not, I mean,
it's the same thing, isn't it?
I agree that what I showed here in this example is that our estimator is resistant to problem in the tails. In the same way,
support is the same thing, surely. Support is just a high-dimensional version of. It's just what happens in high dimensions in the tail. I mean, essentially, a Gaussian distribution is compactly supported on a low-dimensional subspace of where you live, and it's making modeling assumptions that's very, very strong. No, I'm not again. I find it very interesting what you're doing. Don't get me wrong. I just really was asking the slightly more limited question. Which isn't what you're saying effectively that I only really want to use the Gaussian distribution in the non-tail area. But if you only use the Gaussian distribution in the non-tail area, there are going to be other random other distributions which match it in that non-tail area, broadly speaking, and which don't have this aggressive contradictory behavior in the tail. For example, a Cauchy distribution. Maybe that's too extreme in the other direction, but I mean, it doesn't handle a high-dimensional case, actually. So, yeah, I mean, I just wanted, but I mean, actually, to deal with the high-dimensional case, though, none of these approaches do. I mean, so your approach might well be much more effective in the high-dimensional case. Actually.
Yeah, I mean, it's not clear that it always gives the right rate of convergence in high dimensions. So, but the point is still that our method, I think at least that the implementation is quite simple. And once again, I'm not like this question of building a universal estimator is a theoretical question. And I don't think that it means that we should always replace MLE with this. I just say that in some sense, it's a kind of easy to implement method that you can use in any method and that you should at least compare to MLE or to any other ad hoc modelization based on the data. But I also want to insist on the fact that there's something else that seems important to me, is that you can include some information on what is your objective or on like what are likely outliers in your model in the kernel, actually. And I think that this gives you a kind of extra flexibility in some sense, even though it might be difficult to choose it in some cases. But so I think that the simplicity of the method makes it worth to try it and to compare it. And actually, this is what we did in practice. For example, in the Copula paper, we had many examples where we just computed the MLE and on real data and our estimator, and they were very close. But in some cases, there were deviation. And when there is deviation, I don't claim that our estimator is necessarily the one that should be used, but I claim that these cases should be investigated in practice at least. So
can I just make maybe just a short comment? Maybe
yes.
A good way to think about this is this robustness in the sense of Huber. This is really defined not really in terms of outliers or anything like this. It just says add a bit of mass in another measure and add it, to your original measure, and then essentially bound differentiate derivative of it. So the question of, what this means in practice really boils down to what your distance on the space of measures picks up, right? And so this question about whether this must be Gaussian and the tail behavior, this I don't think is so central to it. So it sort of more opens a different question about how to measure distance between measures when you apply the definition of Huber.
But by the way, I should mention actually that our result in the paper is slightly stronger because we wanted to write a result in the Huber contamination model because it's classical, but we also wrote a result in the adversarial case. So the adversarial case, is the situation where there is a set of points and you are about to use a method. For example, you say, I'm going to use MLE, or I'm going to use tail correction with Cauchy distribution, or I'm going to use MMD. And actually, you have an opponent, and the opponent who knows what method you are going to use is allowed to replace a proportion epsilon of the observations by absolutely whatever. Okay, so in particular, the opponent could do some random sampling from Q. So in this case, actually, you see that the adversarial contamination model is more general than the Huber contamination model. But actually, the adversarial contamination model is more general because it can it covers the case of a malevolent opponent who would try to fool the statistical method you're using. And actually, we prove in the paper a similar result in the adversarial contamination model. So that's worth mentioning this. Do I still have a few minutes to cover the dependent case?
Sure.
Okay, thank you. So just the idea here was quite simple. I mean, we know that many methods were used to study estimation of models where you have dependent observation. But here, actually, if you just come back to the definition, sorry, to the proof of the convergence of the estimator, if you don't assume anymore that the xi are independent, then instead of 1/n in the distance, the square distance between the empirical distribution and the truth, you obtain 1/n plus a series of covariance in the Hilbert space H. And I think this is, it's interesting because then actually, if you want to write an assumption on the dependence of the data, that would be as general as possible, but in order to ensure that the previous proof would still work, you simply have to assume that the covariances between two observations like decay fast enough with time, but not the covariances of the xt, but the covariances of the xt injected in the Hilbert space, actually, mapped in the Hilbert space. So actually, simplest way to write that is just to summarize the previous calculation by saying that the distance, when you write rho h as the absolute value of the expectation of the covariance in the Hilbert space, then actually now the rate of convergence is 1/n times 1 plus the sum of the rho h ranging from 1 to n. Okay, so you obtain exactly the same result as before, but this time the rate is replaced by 2 plus 2 times the sum of the covariances over n, of the square root of n, sorry. So of course, you recover the independent case by taking the rho h is equal to 0. Okay, but like for example, when the covariances in H are summable, then you obtain something that still converges at the rate square root of n. There are results in probability and not in expectation, but it's just technical. Maybe it's not the most interesting. What I wanted to do finally is to compare this assumption. I think that this assumption that the covariances are bounded in the Hilbert space, here it seems natural just because it's you can plug it in the proof. But apart from that, is it a natural assumption or not? We should, of course, check it on examples. And the point is that there is a very rich literature. Many people proposed many variants of the covariance coefficients. And each time it's more or less always the same. Like you have a coefficient, and this coefficient characterizes the dependence between xt and xt plus h. And if this coefficient decays fast enough with h, usually in the sense that they are summable, then you recover the usual like law of large numbers, central limit theorem, and from this you can prove that many estimators are consistent. This estimator, like these coefficients, are alpha mixing, beta mixing, phi mixing, etc. And at least we wanted to compare this coefficient to the usual ones, just to see what it gives. So we first started with an example. Actually, if you have if the xt's are not i.i.d, but they are autoregressive in RD, so xt plus 1 is a times xt plus some noise, and a is some matrix. Actually, for example, in this case, you really need minimal assumptions to prove that the covariances in the Hilbert space, when you use the Gaussian kernel, are small. The Gaussian kernel is Lipschitz, and actually this result would stand for any L Lipschitz kernel. The assumption that you need are simply that the epsilon, the noise, is summable, so the expectation of the norm of epsilon is finite, and the largest eigenvalue of 1 is smaller than 1, strictly. And in this case, the rho t decay in largest value of a to the t So they decay to zero exponentially fast, and so they are summable. So actually, it means that in a very large class of autoregressive models would satisfy our assumption. And interestingly enough, actually, it includes a case that is quite famous actually for people working in this like alpha and beta mixing thing. Just like you draw x naught as a uniform on 0, 1, and epsilon t, the noise is Bernoulli random variable. And you take xt plus 1 is xt plus eta t plus 1. So this process is quite known because actually it's autoregressive, it's very simple, but usually it does not satisfy these mixing conditions. The reason why is just that you see actually if you see xt as a number written 0.0110, so like binary digit expansion of a real number between 0 and 1. Each time, each step of the process, you just shift the expansion to the right and include a random digit between the dot and your expansion. And it means that actually it's a special case of the previous, because it's an autoregressive process, it's a special case of the previous proposition. So the covariances in the Hilbert space corresponding to the Gaussian kernel are in 1/2 to the t. But on the other hand, actually, the process is known to be non-alpha mixing or non-beta mixing because the reason is that xt is a deterministic function of xt plus h. And these coefficients are symmetric usually. And when one of the two variables is a deterministic function of the other, you have a very strong dependence, so they don't go to 0. So if you use results on alpha or beta mixing, you don't have, you cannot prove the limit result for this, even though actually it's quite, in this case, it's quite simple to prove that it will satisfy law of large numbers, etc. Well, anyway, our coefficients rho t in this case go to 0 exponentially fast, which means that if your observations have that kind of dependence, then you would recover a consistent estimation as in the independent case. And more generally, we also prove that the coefficient is, in general, under very general assumption on the kernel K, the rho t remains always bounded by the beta mixing coefficient. So it's nice because it means that even if your independence assumption is, you're not completely sure of it, you still have some guarantees for the estimation method.